What is laminar flow? Laminar flow is a concept in fluid dynamics which describes the smooth and orderly movement of a fluid, liquid or gas. In laminar flow, fluid particles move in predictable, parallel layers with minimal mixing between layers. Each layer of fluid flows smoothly past the adjacent layer. And why we need to learn about laminar flow? Laminar flow is essential in various fields for several reasons, such as in engineering design, biomedical application, aerospace, and fluid dynamic research. For instance, in engineering design, engineers need to consider fluid flow, including laminar flow when designing systems such as pipelines, heat exchangers, and chemical reactors. What is laminar flow in detail? Laminar flow is a type of fluid flow characterized by smooth, parallel layers of fluid moving in the same direction with little to no mixing between the layers. In laminar flow, the fluid particles follow a regular and organized pattern, and the flow is characterized by low turbulence. This is different to turbulent flow, where the fluid moves chaotically with irregular fluctuation and mixing. The transition from laminar to turbulent flow often depends on different factors, such as the velocity of the fluid, the viscosity of the fluid, and the size and shape of the conduit through which the fluid is flowing. Laminar flow is often observed at lower fluid velocities and in situations where the fluid viscosity is relatively high.
Theory. Based on the description that I have provided about laminar flow, the most important part that we can conclude is laminar flow is characterized by a smooth and orderly movement of fluid. The fluid moves in parallel layers or streamline. The velocity of the fluid remains constant along any given streamline. Laminar flow is associated with well-defined and predictable flow path. Laminar flow typically occurs at lower flow velocity or in situations where the fluid has high viscosity. Laminar flow is often observed in small diameter pipes and in flows characterized by low Reynolds number. Figure shown in the slide is the laminar and turbulent flow across a flat plate. Development of boundary layer. As the fluid approaches the flat plate, the velocity of the fluid particles at the surface of the plate is zero. The layer of fluid in immediate contact with the surface is called the boundary layer. Formation of velocity profile. Within the boundary layer, the velocity of fluid particles increases gradually from zero at the plate surface to the free stream velocity away from the surface. The velocity profile in the boundary layer is parabolic for laminar flow, with the maximum velocity occurring at the center of the layer. Reynolds number. For laminar flow over a flat plate, the Reynolds number is low. At low Reynolds number, the flow is typically laminar, and the boundary layer remains thin and well organized. Objective. First, to determine the effects of different airflow velocities on the profile of the boundary layer form. Second, to learn how to set up the CFD simulation. And the last one, to compare the result of different airflow velocities. Geometry, details, and dimensions. In this simulation, we will create a 2D plane model with a horizontal line 0.5 meter and vertical 1 meter. We will be considering an internal laminar flow, and the two values of airflow are 2 meter per second and 2.5 meter per second from the inlet.
So now I have a blank template of fluid flow forms here. So first I need to right click on geometry and click on new design modular geometry. And the first thing I need to do is to do some setting here. Setting, I click on show in 2D, snap, measure spacing, I will assign as 0.1. And then minus step per measure, I will assign as 10. So to generate a 2D model plane, so I just click on Z axis here. So we can see the plane here. So next we're gonna draw the rectangle. So I click rectangle, so I draw just roughly here first. Okay, so we can see the rectangle here. The bottom line is going to be our plate, and what you can see, everything you see here is going to be the air. The left side is the boundary, the right side is other boundary, and the top surface is going to our third boundary. So next things we're gonna do is I would like to assign the dimension here. So the horizontal line I assign as 0.5 meter. Okay, the vertical line I would assign as 0.1 meter. Okay, so you can see here our surface here, our plane, 2D plane. So next step is going to do is generate surface from the sketch. So I just click on concept, surface from the sketch, click on sketch 1, and then apply. and then we're gonna click on generate. So what you can see here, what you can see in the gray here is actually the air. The bottom boundary here is our plate. The left boundary is where the flow is entering here. So this is the inlet, and the right side is our outlet. So the flow eventually will be leave. We can just assume that constant pressure boundary left at the end. So I will finish our geometry. So I would like to save the project. So when I click mesh generator, it will execute another package for me to create 2D mesh. So I go to 2D view. Okay, so if I simply click on generate mesh, it's going to generate roughly the worst mesh possible because there is no control default. We cannot use this because it does not have characteristic that we want. For example, we know that near the solid boundary here, near a solid boundary, there will be a huge gradient of velocity, very short changes of velocity here. So we want to have more green point near the surface because that includes the high gradient. Therefore, we need to modify that. So I can click on mesh. So I can insert and then face meshing. So I click on the surface here, apply, generate mesh. Okay, so when I click on mesh, still not that much good, but the lines are now very straight. That's because we have a face meshing. Now again, I want to control the number of grid points that I have on each boundary. I go to mesh, insert, sizing. So I would like to select the edge, top, both line, top and the bottom line. So I will apply, and then now on this information side here, I have different changes. Help me control the number of grid points. For example, I want to control our number of divisions. So number of divisions. So I select 50 here. So I generate mesh. Okay, so here we can see it show you the mesh. There are of course more grid points in both direction, but still it's not giving me the clustering of just near the solid boundary that I really want. So again, right click on mesh, insert, sizing. This time I select left surface, apply, number of divisions. I will assign as 60. So here is the tricky part, no bias, which essentially is going to generate a uniform mesh for me, but I do want the mesh to be biased, so I can select, for example, this. So bias factor is actually the ratio of the larger cell over this smaller cell. Let's just put 70 here. So we're gonna generate mesh. So we click on mesh. Okay. So as you see on this schematic, I expect to have more cluster mesh here, and mine cost mesh, that's what I want, kind of what I wanted, but it's not a uniform and pretty mesh. I want all the knots to be across it, close to bottom here. In order to do that, I would do another sizing. So now I choose the right boundary here, apply, the same thing as a left boundary, number of division 60, and then bias type same as left boundary. So bias factor I'm gonna assign at 70, and as you can see here, there is small to cos gain, so I choose the reverse bias, apply reverse bias here. So now we click on generate mesh. So when we click, it's very quickly to generate this mesh because it's very easy. Now this is a pretty good mesh for my configuration, because if I zoom in, here you will see that there are very small grid points near gradient of velocity is actually really using. So at this point, I have done my mesh. In the next step, before I proceed to defining in the simulation, I have to assign some names. So first, selecting the surface, right click the surface, right click. So I would choose quick name selection. It's a way that we kind of tag different parts of model. This text will later be used in the simulation flow. So we select the edge here. So name of selection and flow. So the edge here, right click, create name selection, we assign as inlet. Okay, and the same thing we assign as right boundary as outlet. So click OK, and okay, so this surface is my plate, so I click on the surface. So I click name selection, plate, then I click OK. The last one is our top surface here, so I click top surface, right click, click name selection. This one does not really matter much because it's going to be far away from the plate, but just for the course, so we assign this as far field pressure here. So click OK. Now we done our mesh here.
When we press on the tag, it will come out this one. The software will look into the mesh, and when it show is done, then that means it's a good meshing. Then we also can check the report quality. The report quality shows the quality of the mesh, and it will give the error and advise if we do some error when we are meshing. Later that we should click on models, then we should click on the viscous. We should change into laminar as we are doing laminar now. Then we will click OK. Next, for the materials, we will click the air. Then we should change the density to 1 and the viscosity to 1 to the power of -4, 10 to the power of -4. Then we should click the change or create, and we close it. Later that we should click on the cell zone condition, and there's nothing here, and we maintain it. And for the boundary condition, first the plate The plate is the stationary wall and no slip. No slip means that the velocity is 0, and we should maintain this one, and we close it. Next, we click on the inlet. We should identify the velocity specification method, which is magnitude normal to boundary, and the velocity magnitude we should use 2, and we do the two velocity at the inlet, which is 2 and 2.5. So we should do for the 2 and the 2.5, and the supersonic or initial gauge pressure we just put 0. We click apply, then we close it. Next, for the outlet, we should make sure that the gauge pressure is 0, which means that it is atmospheric pressure at the outlet. And the backflow direction specification method, we should make sure it is normal to boundary, and we close it since there is no change. The far field pressure. For the far field pressure, we should change the type to symmetry, and then we click apply, then we close it. Next, we should look at the solution, and we click on the methods. The scheme for pressure velocity coupling we choose is simple. Then we should make sure the pressure is second order and the momentum is second order upward. Next, we should look at the controls. This is the constant, then we shouldn't change it. We should change the monitors, the residual, we should change the continuity x velocity and y velocity into 1 to the power of 10 of negative 6. Then we put OK. Next, for the standard initialization, we should change into standard initialization and compute from the inlet. Then we should make sure that the x velocity is the velocity that we just put just now, which is 2. Then we initialize. Next, we should run calculation. Number of iterations that is impossible to be 0, so we change to this one. And the reporting interval is 1. Now we can click on calculate, and we should wait for the graph to come out. The skew residuals, the x-axis represent the iterations, the number of iterations, and the y-axis represent the residuals. We should take some time for the skew residuals graph to come out. This will take some time as the number of iterations is many. Now it shows that the calculation is complete and we click OK. Next, we will go to the monitors and click on the residual. We need to change to the 1 times 10 to the power of negative 7. This one also the same. And the Y velocity also the same. And we click OK. Next, we need to calculate. Then we should click OK. Now it will do the same thing, and we need to wait just because just now we changed to 1 times 10 to the power of negative 7. Now the calculation is complete and we will click OK. Now we will click File, Save Project. Now we have two methods to look at the result, which is click on graphics here or solution here. We just click on the graphics and we look at the contours. We choose for the velocity and save or display. Then we close it. The color bar on the left, the color bar is on the left, and the red color having the bigger velocity formation of the boundary layer on the plate. If we can see, there is some colors under here, but the red color is almost have the largest space. That means that the red color having the larger velocity. Or we can click on vectors of velocity, and we click save or display. This shows that the vectors. Next, we also can increase the scale to 5. Then we can see like this. There is another color at the bottom, and we should click on path lines. We also can click on path lines, and then the particle variables. We choose inlet, save display, close. It shows this one. There is many colors under here. Then file, save project, OK. We need to wait until it is saved and we can close it. And this is the results for counter plot, vectors, path line. We can see there's different color, and last the red color having the bigger velocity or the larger velocity.
This is the result obtained. On the left hand side is for 2.5 meter per second, while on the right hand side is 2.0 meter per second. Velocity counter use a color scale to represent different velocity magnitude. Based on the result, The orange or red color above the flat plate indicates higher velocity, while the blue or green color at the bottom represent lower velocities.
Now we can see the orange color is the higher velocity in the profile. Then we can relate it to the theory, as the laminar flow is characterized by predictable and well-defined flow path with fluid particles moving in organized manner. We can see that the line in the counter plot, it is well plotted and it is organized manner. It typically occurs at lower flow velocity or in situation where the fluid has high viscosity. Laminar flow is often observed in small diameter pipes, low Reynolds number flow, and viscous fluids. And this is the profile of the boundary layer. And we can see that this is the counter plot for the 2.0 meter per second velocity, and this is the counter plot for the 2.5 meter per second. And then we can see for the 2.5 meter per second, we also can see that the counter plot is plotted in a manner way. The effects of the boundary layer on the flow of air depend on its thickness. A thin boundary layer has little effect on the flow of air, but when it is thick, it can cause the airflow to become turbulent and unstable. This can create drag or resistance to the movement of the object, which can increase the amount of energy needed to maintain the motion. The boundary layer can also create separation where the flow of air is disrupted and does not follow the surface of the object. This can cause the object to lose lift or become unstable, so we can conclude that when it is thickened, it can cause the airflow to become turbulent and unstable. Next, the velocity. The velocity profile describes the spatial distribution of instantaneous velocity vectors across a given cross-section. Higher velocity experiences larger in magnitude in the middle of the profile due to the effect of friction. The level of friction is quantified by a parameter called the roughness length. Streamlines connect velocity and are tangential to the instantaneous direction of multiple velocity vectors. They can be curved and do not always follow the shape of the container. Additionally, they only exist in steady flows, that is, flows whose velocity vectors do not change over time. In a laminar flow, all particles of the fluid are traveling in parallel lines, which give rise to parallel streamlines, while in a turbulent flow, particles are traveling in random and chaotic directions, which give rise to curved, spiraling, and often intersecting streamlines. So we can conclude that the higher velocity experiences that, for example, the 2.5 meter per second velocity, it will experience a larger in magnitude in the middle of the profile because the effect of the friction compared to the 2.0 meter per second.